Hello and welcome to ninth session of the course Power Plant System Engineering. So, I'm going to start the session. Let me go to the slide first. Okay, so first let me share the screen. Okay, so I suppose my screen would be visible to all of you. Anyway, nobody has joined yet. So I am start the session. Meanwhile, anybody can join in between. Okay, so let me go to the session. Okay, so this is ninth week of the course of Power Plant System Engineering. In this week, we have learned about the gas turbine cycle, which is Brayton cycle, and have solved different numerical based on that. Okay, so we take some pen. Okay, so in the past week, what we have covered is the fundamentals of the gas turbine, in which fundamentals of gas turbine power system, in which we have learned about the gas turbine cycle, which Brayton cycle, and thermodynamic analysis of the Brayton cycle. Then the different modifications of the Brayton cycle and the non-ideal cycle, the regeneration, the non-ideality in the Brayton cycle comes due to the non-isentropic nature of the isentropic processes in the ideal Brayton cycle. Then the modification like regeneration, then compressor in cooling or okay, compressor intercooling means we compress the air in different in the different compressors. Okay, so or we can say the multi-stage compressing. Then the turbine reheating. What's happening to this? Okay, then the turbine reheating and water injection, something like that. Okay, and then the combined power cycle, the background concepts, combined cycle power plants, exergy and energy analysis. Then a different turbine for aircraft propulsion cycle, turbojet engine, and aircraft engines, and then we have solved assignment number 9. Okay, so if you will look at the topics covered in the past week, that is vast, and in the 2 hours session, it is not quite possible to cover all those things. So this session would be focused on the gas turbine cycle and specifically on the Brayton cycle and its modifications, like the non-ideality and regeneration, compression intercooling, then turbine reheat and water injection. Okay, so the aim of the session would be the same. I will give the quick summary of the topics covered in the past week. Then I will solve the assignment problems. Okay, and if somebody will join and he or she will have some doubt, then we will take that out, those doubts also. Then I will start with a summary of the topics covered in the past week. Okay, so we will start with the Brayton cycle. Mm, check. Okay, so let me start with the Brayton cycle. Brayton cycle. Basically, it the Brayton cycle is of two types. First one is the open Brayton cycle. Open Brayton cycle, and second one would be the closed Brayton cycle. Things you will get to know in the pictorial view, or the block diagram of the different Brayton cycles. Okay, so let me draw first. The Brayton cycle is have the open Brayton cycle have majorly three components. This compressor, I will denote it with the help of C. Then it has a shaft, okay, which connect to the turbine T. Turbine T. Basically, this shaft means that this compressor is run by this turbine mechanical work output. Okay, then in this, okay, so air enters the compressor from here, and the compressor compress the air and send it to the combustion chamber. I will denote it with CC. Then this compressed, this high temperature air is sent to the gas turbine. It expanded in this gas turbine and then out from the turbine. Okay, so me say this is point 1, this is point 2, this is point 3, and this is point 4. So here we can say that the air exit from this point 4, and it is nothing to do with this the air which is going to enter from point A. So this is some sort of the open cycle where in every cycle the fresh air enters into the compressor. Okay, so let me say the name, the open Brayton cycle. Open Brayton cycle. Okay, here let me say C is the compressor, P is the turbine, and CC is the combustion chamber. Okay, this is the nomenclature for this. And in the closed Brayton cycle, let me draw it here. So this is the compressor. So like this is the air entering here at point 1. Then it got compressed and then sent to a heat exchanger. Then it got heated and then expanded into a turbine. Basically, this compressor would be connected to this turbine. Basically, it would be run by the help of this turbine. So, okay, this is point 2, this is point 3, and air is exiting here at from point A. This is compressor, this is turbine, and this is some sort of heat exchanger. This is the heat exchanger, and then the air exiting from this at point A release the heat in this intercooler, and then the same air fed to this uh, same air, or we can say and any gas is fed to the compressor at point 1. So this is intercooler. So intercooler. This is HE means the heat exchanger. This is the heat exchanger, and this is the type of closed Brayton cycle. This is kind of first, and this is kind of second. This is the closed Brayton cycle. Closed Brayton cycle. Okay, so the thing is that this Brayton cycle, we supplied the heat from here in the combustion chamber QS, and it is some the heat released here QR if we connected it by some imaginary line. So heat is exiting from here. Similarly, heat is supplied from this heat exchanger, and heat released, the excess heat is released in this intercooler. We have to supply some compressor work to the cycle here, and we got the this turbine work from here. Similarly, we have to supply some compressor work at here in the compressor, and we will get some turbine work from the turbine WT. So these are the open and closed Brayton cycles. Now, generally, it is open Brayton cycle which is used in the gas turbine power plant. So let me draw the same cycle in the TS and PV diagram. So let me draw it here. Let's suppose this is my TS plot, and this is the PV plot. We take another color. So here, basically, the Brayton cycle has two isentropic and two constant pressure processes, similar in the ideal Rankine cycle, but that was with the steam, and this one is for with the air. So on this TS plot, let me draw some two constant pressure lines. Like here, let's suppose these are two constant pressure lines. Okay, this line is denoting the constant pressure P1 is equals to C, the constant pressure, and this line is denoting the P2 is equals to C, the constant pressure P2. Okay, so if this is the point 1, which is entry to the compressor, so process 1 to 2 would be the isentropic compression in the compressor. Then the heat will be added in the combustion chamber from 2 to 3. This is point 3, and the combustion chamber would work at the constant pressure. Then from point 3 to 4, it will get expanded in the tur turbine, this would be the isentropic compression. Oh, sorry, isentropic expansion. And 4 to 1, the it would be the constant pressure heat rejection process in the intercooler. So the Brayton's cycle comprises of four processes from process 1 to 2, okay, which is the isotropic compression in the compressor, 2 to 3, the constant pressure heat addition in the combustion chamber, 3 to 4 is the isentropic expansion in the turbine, and 4 to 1 is the constant pressure heat rejection in the intercooler. The same process we can show in the on the PV plot. So, like on PV plot, this line is denoting the constant entropy line, like the isentropic lines. This is the constant pressure line P2, suppose, and this would the isentropic expansion in the turbine, and this would be the constant pressure heat rejection in the intercooler. So the points would be here are 1, 1 to 2, the uh, isotopic compression in the compressor. 2 to 3 is the constant pressure heat reaction in the combustion chamber. 3 to 4 are the is the isotopic expansion in the turbine, and 4 to 1 is the constant pressure heat rejection in the uh, intercooler. Okay, so here, as we have said, this is the constant pressure line, the P1, and this is the constant pressure line P2. Okay, and here from point 1 to 2, the compressor work WC will get consumed. Here, the heat QS heat supplied would be there in the combustion chamber. From 3 to 4, we will get the turbine work WT, and from 4 to 1, the heat rejected would be QR in the intercooler. The similar we can show here, it would be WC, the heat supplied QS, the turbine work WT, and the heat released or heat rejected QR. Now we can apply the heat balance equation. The heat balance equation in would be equals to E out. So here the heat or the sorry, this won't be the heat balance equation. This will be the energy balance equation. Energy balance equation. So energy in would be equals to the energy out. So here the energy in is the WC and QS. So these are the input form of energy. So the compressor work plus heat supplied would be equals to the turbine work plus heat released. If we rearrange this thing, then we will get QS minus QR is equals to WT minus WC. Okay, let me call it equation number 1. So equation number 1 is saying that the net heat will be equals to the net work. Okay, so after this, I will write the expression for compressor work and turbine work, the turbine work output, and the heat released. Okay, so let me write it one by one. So one would be the process. The first process would be process 1 to 2. And what it is saying, it is the isentropic heat, the isentropic compression of the working gas in the compressor. So here we have to find out the what will be the compressor work. Compressor work WC will be what? So here WC would be so the value of compressor work would be enthalpy at point 2 minus enthalpy at point 1, H2 minus H1. And for the gas, the enthalpy H is the CPT. For the ideal gas, H would be the Cp into T, and T is the temperature in the Kelvin. Okay, let me club it here as this is not the part of any expression. Okay, so the value of WC would be Cp into T2 minus Ty. So this would be my pressure work. Equation number 2 I would write. Next, the process number 2, the process 2 to 3. Process 2 to 3. And here we have to calculate the heat supplied equals to what? So QS would be, here we will say the heat supplied would be the enthalpy at point 3 minus enthalpy at point 2. So QS would be the H3 minus H2 is equals to Cp T3 minus, write it more clearly, Cp T3 minus T2 would be the equation number 3. Process 3 would be the process 3 to 4, and it is the turbine work output. Turbine work would be what? So WT would be H3 minus H4 is equals to Cp T3 minus T4 would be my equation number 4. And the last process would be the heat release. Heat release would be QR is equals to H4 minus H1, which would be Cp T4 minus T1. These are the four equations from equation 2 to 5, by the help of which we can calculate the heat and work interaction in the different processes from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So now let me write it clearly. This is process 4 to 1, and this is the heat release, rejected or release. Okay, so here in the another way we can write the network output. W net would be WT minus WC, which was WT is H3 minus H4 and WC was H2 minus H1. If we will rearrange this thing, then H3 minus H2 minus this is minus H1 minus H4. This is the value of this S3 minus S2 is the value of heat supplied QS minus H1 and minus H. Okay. Minus sign would be there. This would be the H4 minus H1. Okay. This would be the H4 minus H1. So this is the expression for the rejected heat. So from here, we also get the network interaction is equals to net heat interaction. Okay, the same we will get as the equation number one. The same we got as the equation number six. Okay, so these are the some sort of derivations we got. Next, let me define some terms which we used in the design of a Brayton cycle and also to characterize a steam turbine, sorry, Brayton, the gas turbine or the Brayton cycle. And the first parameter is the pressure ratio. Pressure ratio, we denote it by RP. Okay, so RP is defined as the ratio of the upper pressure to the high pressure to the lower pressure, as this Brayton cycle is all about the two isotopic and two constant pressure processes like this, like one, this is point two, three, and four. Okay, so here, like this process is at pressure P1 and this process is at pressure P2, then the value of the RP would be the ratio of upper pressure to the lower pressure, the P2 by P1. Okay, so my uh, pressure ratio would be defined like this, and I will denote it by equation number 7. Okay. Okay, so this was my question number 7, the definition of the pressure ratio. Next, we can also have some relationship between this temperature T2 by T1 and this T3 by T4. So, as my pressure 1 to 2 is isentropic, then I can write this equation. This T2 by T1 would be the P2 by P1 to the power gamma minus 1 by gamma. Okay, and this P2 by P1 is simply defined as the pressure ratio. So it would be the Rp to the power gamma minus 1 by gamma. Equation number 8. Then this ratio T3 by T4, we can also write it like P2 by P1 to the power gamma minus 1 by gamma. So this would also be the pressure ratio to the power minus 1 by gamma. So from equation 8 and 9, from 8 and 9, we can write that T2 by T1 is equals to T3 by T4, or or we can write this T4 by T1 is equals to T3 by T2. I will write it as equation number 10. Okay. Then next, let me uh, derive the expression for efficiency of an ideal Brayton cycle or simple Brayton cycle. Let me put the heading here. Efficiency of a simple Brayton cycle. Efficiency of a simple Brayton cycle. So the efficiency bill would simply be the network divided by the heat supplied. So efficiency of the Brayton cycle would be W net divided by the US. And from this equation, from equation number, okay, the W net would be WT minus WC divided by heat supplied QS. From equation number 1, we have seen that WT minus WC would be QS minus QR. So let me go to the next slide. Then eta B would be QS minus QR divided by heat supplied QS. This would be 1 minus QR by QS. Okay. Now from equation number 3 and 5, we can write the expression for the this QS and QR, and that would be the 1 minus Cp into T4 minus T1 divided by Cp into T3 minus T2. This is simply from equation 3 and 5. 3 and 5. Okay. So this CP would be cancelled out with this CP. Let me take the common T1 from the numerator and T2 from the denominator. Then 1 minus this would be the T1. Then inside would be T4 by T1 minus 1. This is T1. And inside it, and the T2 I will take out, then T3 by T2 minus 1. So as I have seen from equation number 10, from equation 10, it is T4 by T1 is equals to T3 by T2. Then this thing also will get cancelled out. Okay. So now eta b would be 1 minus T1 by T2. Now I know that because T2 by T1 is equals to Rp to the power gamma minus 1 by gamma, then the efficiency of the Brayton cycle would be 1 minus 1 upon pressure ratio to the power gamma minus 1 divided by gamma. Okay. So this expression would be my expression for the efficiency of an ideal Brayton cycle. We will note it by question number 11. Next, another important parameter, which is the back work ratio. Back work ratio. We denote it by RBW, and it is defined as RBW is equals to the ratio of compressor work to the turbine work. Question number 12. Next parameter comes the work ratio. Work ratio RW is defined as the net work divided by the turbine work. The net work is WT minus WC divided by WT, which would be 1 minus WC by WT, which is nothing but the back work ratio RVW. So the work ratio would be 1 minus the back work ratio. This would be the equation number 13. Now, next parameter would be the air rate. Air rate is simply defined as the mass flow rate of air or 1 kilowatt of power generation. Would be m dot a divided by p. So here the unit of this m dot a is kg per second and the unit of this p is kilowatt. Okay. So the unit of this air ratio would be kg per kilojoule, because what is itself kilojoule per second. So second from this second from this second would get cancelled out. So the unit would be kg per kilojoule. We know that this power would be the mass flow rate of air into the network from the turbine, the network from the cycle. Okay, so from here, the m dot a divided by p would be w net. Okay, the reciprocal of the w net. So from air ratio would be 1 by w net. The unit would be kg per kilojoule, or if we want to convert it to kg per kilowatt hour, we have to simply multiply by 3600. So in that case, air ratio would be 3600 divided by W net. Now the unit would be 36 by W net. Unit would be kg per kilowatt hour. So this would be, if I am calling this one equation number uh, 14, then this would be my equation number 15. So these are the important parameters which I wanted to explain. Next, there are two things: the pressure ratio for the maximum efficiency, pressure ratio for maximum efficiency. Okay, this is the RP max, and it is defined as the this expression T max by T min to the power gamma by gamma minus 1. Equation number 16. Next is the optimum pressure ratio. The optimum pressure ratio for maximum network, maximum net work. So this is the RP optimum, and it is the square root of RP max, or in the other words, it would be the T max by T min to the power gamma divided by 2 into gamma minus 1. This would be the equation number 17. And the optimum efficiency with respect to this pressure ratio would be 1 minus under root of T min by T max. Okay, so these 18 relations will help us uh, to find out the performance of the uh, gas turbine cycle. Next, there are different modifications occurs in order to improve the performance, or we can say work output of a Brayton cycle. So first one is the regeneration. I will write the heading modifications to the ideal Brayton cycle. First is the regeneration. First one is the regeneration. Regeneration is nothing but to extract the heat from the flue gases and transfer this heat to the uh, air which is entering into the compressor. Okay, so we will understand this regeneration from this TS diagram. Okay, let's suppose this is the TS diagram of the Brayton cycle. Okay, this is T, this is S, this is point 1, 2, 3, and 4. So here we can see that this point 4 is above than point 2. So we can transfer some heat from the air which is leaving the steam turbine at point 4. We can supply some heat to the compressed air which is leaving from the compressor. So let's suppose from point 4 to A, this steam has transferred some heat to this incoming steam to the combustion chamber, and it reaches at point B. Okay, so by transferring some heat, uh, uh, the turbine exit point moves from point 4 to point B, and by gaining some heat, the compressor exit point moves from point 2 to point A. Okay, this is called regeneration. So in this case, the turbine work will be the same with and without regeneration. The compressor work would be the same with and without regeneration. The QS and QR will get changed. So um, the original original QS was H3 minus H2, and the modified would be modified QS test would be H3 minus HA. This is my modified heat supplied and modified heat rejected. Now the original heat rejected QR was heat rejected QR was H4 minus H1. Now modified, heat rejected, QR dash would be QR dash would be HB minus H1. And here comes a performance parameter, which is the effectiveness of the regenerator. Let me write it here. Effectiveness. Effectiveness would be effectiveness is equals to TA minus T2 divided by T4 minus T2. Basically, it is the difference of maximum temperature, the actual temperature from the maximum temperature at which this point 2 could get reached. So this point 2 could get reached to point 4, but it is reaching to point A. So this would be the ratio of Ta minus T2 divided by T4 minus T2. This is called the effectiveness of the regeneration. Then second modification comes as the intercooling. As the intercooling. Second modification comes as the intercooling. So this is the thing when we compress the entering air in the multiple steps. Okay. So the TS diagram for this intercooling. Let me plot the equation first. Suppose this is TS diagram and this is the PV diagram, and these are the three pressures. These are the three constant pressure lines. Okay. And let us suppose the state is start compressing from this point 1 to point 2. Okay. Then, okay, let me erase all the things first. So it is the multi-stage compression thing. All right. So like this is the air compressed in the first compressor, then it is compressed in the another compressor. Then the heat added in the combustion chamber is expanded in the turbine and then heat is released here. Let's suppose these are three pressures. Pressure 1, this is pressure 1, this is P1 is equals to constant, this is constant P2 pressure, and this is intermediate constant pressure. Okay, this is point 1. So point 1 to 2, it is compressed in first compressor, then it is cooled down at intermediate pressure PC to reach at point 3, then point 3 to 4 it is compressed into another compressor, then 4 to 5 the heat is added in the combustion chamber, then 5 to 6 it is expanded into the turbine, then 6 to 1 the heat is rejected. Okay, the same we can plot onto the PV cycle, and the PV plot. So from This is point 1 to 2. It is compressed in first compressor, then 2 to 3. It is intercooled at intermediate pressure Pi, then 3 to, let's suppose, let's say 4. It is compressed in another compressor. Then it is the heat added into the C from 4 to 5 and expanded into the turbine 5 to 6. Then the is rejected from 6 to 1 in the intercooler or heat exchanger. Okay, so this would be the uh, cycle on the PV plot. So here would be the same thing. So here this this negative work would be saved, and by the help of this intercooling, the network is increased because W net is the WT minus WC. So here, let me write the things. This is WT, this is WP1, WP2, QS, QR. Similar here, WP1, this is the WP2, this is the QS. Sorry, this is QS, QS. This is WT, and this is WR, heat rejected. So here we can see the WT is same while the pump work is decreased. So as the pump work is the compressor work is decreased here, the network will get increased. Okay, the network will get increased. So here W net is increased by the help of intercooling. However, the efficiency will get decreased, but W net will get increased. Next, the reheating. The third process is the reheating. Let me write under the points for perfect intercooling. Perfect intercooling. For the perfect intercooling, T1 is equals to T3. This is the first point. Then the intermediate pressure would be the geometric mean of the two pressures. Geometric mean of the two pressures P1, P2. Okay. The second point, the compressor work for both the compressors would be the same. WC1 would be equals to WC2, and T2 would be also equals to T4. So these are the conditions for the perfect intercooling. Then third is the reheating. Third modification is the reheating. Okay. In the reheating, the gas expanded into the turbines in different stages. Let's suppose this is the TS diagram, and this is the PV diagram. Okay, so how this will go? So here the air would be compressed in single stage from 1 to 2. When heat is added, then it is expanded in one turbine, then heat is again added, then it is expanded into the second turbine, then the heat is rejected. So 2 to 3, the heat added in the first combustion chamber. 3 to 4, the heat is expanded in the first turbine. 4 to 5, the heat is expanded into the second combustion chamber. 5 to 6, it is expanded in the second turbine. Okay. Then 6 to 1, the heat is rejected. If we draw this thing in the PV diagram, then it will be like this only. Okay. This is 1, 2, 3, 4, 5, then 6. So, like suppose this is the intermediate pressure, Pi is equals to C. This is pressure P1 constant pressure, then P2 constant pressure. The same pressure we can show here. The P1, this is Pi, this is P2, this is P1, P2, and this is somewhere here Pi. So for perfect reheating, the same thing would be there for perfect reheating. The T5 will be equals to T3. Okay, then Pi is equals to under root P1 P2. So here also the intermediate pressure would be the geometric mean of two pressures. Then T4 is equals to T6, and both the turbine works would be the same. WT1 is equals to WT2. So these four are the same conditions for the perfect reheating. So here are the four conditions for the perfect intercooling, and here are the conditions for the perfect reheating. So by this I will stop the theory part. Okay, rest of the things the you can read it by yourself. Now I am moving to the assignment problems. Okay, so the assignment problems are like this. This first problem is saying like when the cooling and heating are done at constant temperatures, and intercooling and reheating stages with the rest of the cycle being ideal in nature for the Brayton cycle, then this representation and this represents as the Ericsson cycle. Okay, so in the Brayton cycle, instead of constant pressures, it uh, if it would be the constant temperature, then that cycle would be the Ericsson cycle. Second one, the ideal cycle used for gas turbine power output is known as the Brayton cycle. The statement is correct from the this lecture. We are talking only about the Brayton cycle, so this statement would be the true statement. Third one is the And the working fluid for a gas turbine power plant operating with Brayton cycle needs to be chosen from four gases: air, nitrogen, carbon dioxide, and helium. With same initial and operating conditions, the best working fluid for the lowest optimum pressure ratio would be the helium. Okay, and that depends on the gamma value. So the lowest optimum pressure would be for the helium only. Then four regenerators are introduced in an non-ideal Brayton cycle to improve the efficiency, but it does not increase the power output. For this statement is true, as we have seen in the regeneration here. Yeah, here. Here is the regeneration. So here we can see the WT is same, WC is same. So the network would be the same. Only the efficiency will be increased as the heat rejected is increased, heat rejected is decreased, and the heat added is decreased. Okay, so both the things are the heat supplied is uh, decreased. That is why the efficiency will be increased and no effect would be on the network output. So this statement is true. Uh, the next is the in the multi-stage compression with intercooling and multi-stage expansion with reheating in a gas power plant is intended for only to uh, increase the output power. The cycle efficiency is not increased in the multi-stage expansion with reheating and intercooling. Okay, so this we can prove from the derivation, or we can look it in different way. Like here we are increasing the heat supplied. Okay, uh, and for the same heat we can't get the equal amount of work output. So that is why the overall efficiency will get decreased. Only the power output will get increased. So as we can say, W net is the difference of turbine work minus compressor work. So in the the intercooling, the uh, compressor work decrease, so the W net increase, and in the reheating, the turbine work increase. That is why the W net increase. So in the multi-staging compression and expansion, the W net, the output power is increased, but not the efficiency. Efficiency will get decreased. Okay. So problem number 6. In a three-stage compressor intercooling in a gas turbine power plant, the air enters the compressor at inlet pressure P1. So let me, it is a three-stage compressor. Okay. Let me draw the cycle first. So this is three-stage compressor. And draw the TS diagram. So this is one stage, will be intercooled, then stage 2, it will be intercooled, then stage 3. Then it will send to the CC, then it is expanded into the turbine. So let's suppose this is my cycle. This is my cycle. Let's number it. And let's suppose this is pressure P1, this is pressure P2. pressure P, constant pressure P1 is equals to P2, constant pressure P3, this is the constant pressure P4, and the numbers are 1, 2, the processes are 1, 2, 3, 4, 5, 6, 7, and 8. So this is the processor. It is given that three-stage turbine intercooling in a gas turbine power plant. The air enters the compressor at P1. The discharge pressure is P4, and the intermediate pressures are P2 and P3 as we have depicted here. The total pressure ratio of the compressor, the P4 divided by P1 is given, and this is 10. Also given, and the pressure ratios of all the stages are equal, like the RP stages. RP stage. This is total RP. RP stage is equals to P2 by P1 is equals to P3 by P2 by P4 by P3. P4 by P3. Also given that P1 is equals to 100 kPa. Okay, so these are the things which are given. So from 1, we can write this equation like this: P2 by P1 into P3 3 by P2 into P4 by P3. So this rearrangement would be the same. P2 will get cancelled by P2, P3 by P3. So this overall this P4 by P1. And okay, so and all these things are having the value of RP, 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 RPS, RPS into RPS is equals to 10. So from that, RP is equals to 10 to the power 1 by 3. Alright. So now we have to find out the value of P3, right? We know that P3 by P2 into P2 by P1 would be RPS into RPS. So this P2 will cancelled out from P2. Then P3 by P1 is equals to 10 to the power 1 by 3 into 10 to the power 1 by 3. So P3 will be 100 into 10 to the power 2 by 3. When we solve it, then value of P3 will come. Okay, so this is 2 by 3. Around 464. 464 kilopascal. So from the this would be my answer. So the value of P3 in kilopascal is 464 kPa. 464.15. Okay. Next, let's move to a series of questions from problem number 7 to 10. It would be quite a big problem. Okay, so let's start this problem. So, it is given that a gas turbine plant consists of two-stage compressor with intercooling and single-stage turbine with regenerator. So, what are the things it is having? Two-stage compressor with the intercooling and single-stage turbine with regenerator. So, we will mention all these things into the TS diagram. Let's suppose my axis TS diagram and yeah, these are the process. And this is first stage, then come like this. This would be the second stage, go like this, single stage expansion, and okay. So like this would be the cycle. Okay, let me draw different pressures. This is P1 is equals to C. This is intermediate pressure Pi is equals to C. This is the upper pressure P2 is equals to C. It is having the regeneration. Let me first put the number. This is one. Okay. So I will guide you with the problem and what they have asked. So this is the point one, two, three, four. This is having some regeneration. So by the help of regeneration, let's suppose that this point four move to point five. This would be point number six. This would be point number seven. And let's suppose by the operation of in the regeneration, this point seven move to point eight. The next thing is that it is having air enters at the compressor at 1 bar and 20 degrees centigrade. Let me write the value first. So the P1 is equals to 1 bar and T1 is equals to 20 degrees centigrade, which would be 293 Kelvin. And the maximum cycle temperature is 900 degrees centigrade and maximum pressure ratio is 6. So the Emax is T6 is equals to 900 degrees centigrade, which essentially would be 1173 Kelvin. Okay, pressure ratio RP is given 6. So because pressure ratio RP is equals to P2 by P1, so 6 would be equals to P2 by 1. So P2 is equals to 6 bar. Okay. The effectiveness of regenerator is 0.7. Effectiveness of the regenerator is 0.7. Okay. And the airflow rate through the plant is 210 kg per second, calorific value 40.8, and the combustion efficiency 0.95. Other values are airflow rate m dot a is equals to 210 kg per second, calorific value of fuel is 40.8 megajoule per kg, and combustion efficiency is 0.95. Next, the isentropic efficiencies for the compressor and turbine are 0.82 and 0.92 respectively. Eta of compressor is 0.82 and eta of turbine is 0.92. All right. Take the mechanical and generator efficiencies are 96% and 95% respectively. Mechanical efficiency is 0.96 and generator efficiency 0.95. Now we have to use Cp of air is equals to 1.005 kilojoule per kg Kelvin, and gamma air is equals to 1.4. The same value we have to use for the uh, combustion products or flue gas is Cpg is equals to 1.08 kilojoule per kg Kelvin, and gamma of gas is 1.33. Okay, so in the seventh problem we have to find the air fuel ratio. Find the air fuel ratio. All right, so for that, first let's just find out the different temperatures. This is zero point 0.5. Okay, let's find out different temperatures. So first we can find out this intermediate pressure PI. So for the for perfect intercooling, this PI would be the geometric mean of P1 and P2. So Pi would be the geometric mean of 1 into 6. So Pi would be 2.45 bar. Okay, this thing we got. Next, as process 1 to 2 is the isentropic process. Okay, let me write plot the non-isentropic process also here. This is my point 2 dash, point 4 dash here, here also. This will be my point 7 dash, which is non-isentropic. Point 7 dash, which is non-isentropic. So for the isentropic process, this T2 by T1 would be the T2 by T1 would be the Pi by T1 to the power. So here uh, the fluid would be the air only. So by gamma air minus 1 by gamma air. So when I will put the values here, then T2 by 293 is equals to 2.45 divided by 1 to the power 1.4 minus 1 divided by 0.4. Then value of T2 will come from here as 378.59 Kelvin. Okay. So as the isotopic efficiency for the combustion is the 0.82, which would essentially be the T2 dash minus T1 divided by T2 minus T1. Here I will put the values. 0.82 is equals to T2 dash we have to find out, minus T1 is 293 divided by, okay, this is T2 and this would be the T2 dash. Okay, so here I have found the T2 value 378.59 and T2 dash I have to find out minus 293 Kelvin divided by 293 Kelvin. So from here T2 dash would be with 397.37 with a 7.37 Kelvin. Now for the perfect intercooling, for perfect intercooling, this T3 will be equals to T1. This T3 is equals to T1 is equals to 293 Kelvin. Okay, and similarly would be T4 by T3 will be P2 by Pi to the power gamma air minus 1 by gamma air. So when we will put the values, all the values here, the value of T4 will come out to be 378.54 Kelvin, and the when we apply the isentropic efficiencies, 0.82 would be minus T4 minus T3 divided by T4 dash minus T3. So T4 dash will come out to be 397.32, 397.32 Kelvin. Okay, next I am having the value of T6. Let me calculate the value of the T7. So the T6 by T7 would be P6, the value of P2 by P1 to the power. Here, the working fluid would be the gas, gamma g minus 1 divided by gamma g. So T6 value I am having 1173 divided by T7 is equals to 6 by 1 to the power 1.33 minus 1 divided by 1.33. When we will solve it, then I will get the value of the T7 as the 752.17 Kelvin. Then I will apply the turbine efficiency. Eta T would be T6 minus T7 dash divided by T6 minus T7. The turbine efficiency we are having 0.92. So 0.92 is equals to T6 value I am having 1173 minus T7 dash I have to calculate. Then T6 value 1173 and T7 value I have just calculated 752.15 Kelvin. So from here the value of T7 dash would be 785.84 Kelvin. Okay. So now I got to know all the temperatures. So next thing, the effectiveness of the regenerator is given. Effectiveness of the heat exchanger can be written here by using this T5 minus T4 dash divided by T7 dash minus T8. So it would be T5 minus T4 dash divided by T7 dash minus T8. No, that was not the correct formula. So effectiveness can be written as T5 minus T4 dash divided by T7 dash minus T4 dash. Okay, so it would be T5 minus T4 dash divided by T7 dash minus T4 dash. Effectiveness, they have provided the value of 0.7 would be equals to the T5 value we have to determine minus T4 dash value we have calculated as 397.32. T7 dash value we have just calculated 785.84 minus T4 dash 397.32. So from here we can get the value of T5 as 669.28 Kelvin. Okay, so as of here we got all the temperatures. Now the next thing we have to do, we have to calculate the air fuel ratio. Okay, so for that, let me draw the combustion chamber CC here. So from here, the mass flow rate of air is coming m dot A, and from here, the mass flow rate of fuel is coming m dot F, and from here, the m dot G is leaving, which is essentially the summation of m dot A plus m dot F. Okay, so this is the thing. This is at temperature T6, this is at temperature T5. So we have to write the energy balance equation for the combustion chamber. Energy balance equation for the combustion chamber. Energy balance equation for the combustion chamber. From beyond this point, I will only hint the how to do the problem, and then you have to try it by yourself. So these are point 1, point 2, and point 3. Point 1, the air is entering. Point 2, the fuel is entering, and point 3, the uh, combustible products are leaving. So energy at point 1 plus energy at point 2 essentially would be equals to energy at point 3. Energy at point 1 is the m dot air into Cp of air into the T5, the temperature at which the air is entering to the combustion chamber. So here it is entering at the temperature T5 plus the heat which is entering from the with the fuel is the m dot F into calorific value of the fuel into the combustion efficiency, which is leaving the m dot A plus m dot F into Cp of gas into the T6. Okay, so this is the equation. These are the things given. CPG, all the things are given. So now let me define the term AMF. What we have to determine? We have to determine the air fuel ratio. Air fuel ratio. AF ratio would be the mass flow rate of air divided by the mass flow rate of the fuel. So I'm dividing this equation 2 by m dot a. So it would be the CPA into T5 plus m dot f by m dot a would be the plus m dot f divided by m dot a into Cv of fuel into eta combustion would be 1 plus m dot f divided by m dot a into Cp gas into T6. This would be equation number 3. So here in this problem, all the values are given. Cp of air is given, T5 we have just calculated, Cp of fuel is given, eta combustion is given, and Cp gas is given, and T6 is also given. So now the unknown term is this. By putting all these values here, we can determine this term. M dot F divided by M dot A would be what? So once we will calculate this, then the air fuel ratio would be m dot a by m dot f. Just reversal of this. Okay, so this would be the answer. All right. Okay. So once we will get the m dot a by m dot f equals to what? This value is given, then we can determine the value of m dot f. Then m dot gas would be the m dot a plus m dot f. This value we can also determine, and we can all we are having all the temperature. So Wt would be m dot g Cpg into T6 minus T7 dash. Wc would be here the fluid would be the air m dot a into Cp air into uh, here it is intercooling. So T2 dash minus T1 plus T4 dash minus T3. This would be T2 dash minus T1 plus T4 dash minus T3. Okay, so by the help of this, we can determine the W net, which would be Wt minus Wc, and Qs we have already know m dot f into Cv into eta combustion. So we will get this value from here, this value from here, then the cycle efficiency would be W net by Qs. So this thing we can also determine. Okay, so these problems are solved. Problem number 8 and problem number 9. Next, what they have asked to uh, determine the power delivered. So power delivered would be W net into mass flow rate of gas. This thing we know, this thing we know, and we can calculate this thing also. Next, what they have asked to specific fuel consumption. Okay, specific fuel consumption. Okay, the specific fuel consumption would be the mass flow rate of fuel divided by the power. This value we are having mass flow rate of not air, mass flow rate of fuel. value we are having and this value we are having. If we are having both the values, then we can determine the value of the S sub c. So I hope this part also you can solve. So these are the problems and the things I want to discuss this session. So thank you.